In Lesson 4.1, Antiderivatives and Indefinite Integration, we're going to essentially learn to undo a differentiation process. Generally, in Chapter 3, we would have a function and differentiate in order to find the derivative. Here in Chapter 4, we're going to take that derivative and find its antiderivative, that is, the family of functions from which that derivative could have come. After we introduce that and look at a few examples of that, we'll talk about some very, very basic integration techniques. That is, integration is the inverse operation of the derivative. It's what I just described, taking the derivative back to the family of functions from which it came. After we're done with all that, we'll take a look at one graphical example, and then we'll conclude these notes by looking at a couple initial value problems. These are problems in which our initial position and perhaps our initial velocity, maybe even our initial acceleration are given. And based off that information, we need to come up with the original function from which all the rest of it sprouts. Usually that's the position function if we're doing a physics-related question, or we could just call it f of x for all it really matters. So anyway, all this being said, why don't we go ahead and begin with some very, very, very basic problems, finding the antiderivatives of some original integrals. Let's take a look. Here in example A, we're given a neat little table to work with, where we're given the original integrand. Notice that the original integrand is actually followed by dx, and that will almost always be the case in this course. What this dx refers to is that we want to integrate this with respect to x. Dx is the differential. It's the tiny little part that represents the width of a rectangle, but we'll learn more about that in 4.2. For now, the dx simply tells us that everything is going to be relative to x. So if we want to rewrite our original integrand, what we could do is move our constant out front. Just like doing derivatives and limits, the scalar constant really doesn't do anything for us. We can move it out of the way, do the work to the rest of the stuff, and then bring the constant back. And that's what we'll do here. Now, having an x on the bottom, we could write this as 1 over x squared. But we're going to find that it's going to be a little bit easier to find the antiderivative if it's written as such with a negative exponent. So how do I integrate this? How can I think about what function, when I differentiate it, would yield x to the negative second? And you can consider that if you like and try a bunch of functions, differentiate each one. You'll eventually find the one with the derivative of x to the negative second. But here's a cool little trick for you. This is the general power rule for integrals. If we're integrating x to the n dx, all we really need to do is raise the exponent by 1 and then divide by whatever our new exponent is. Now, I'm going to write this plus c after. And the reason for that plus c is that every indefinite integral, that is, every integral that just has this sign but doesn't have bounds on it, and we'll learn about that later, but for now, just go with it. This is an integral without bounds. It's an indefinite integral, and that must always end with a plus c. We'll explain why when we get to example B, but for now, again, we'll just go with it. So, if I want to integrate this thing, I'll just leave my 3 outside, and following my general power rule for integrals, I just need to raise the sign, or rather raise the exponent of x by 1, and then divide by that same value. And of course, I'll keep my plus c with it, so that when I simplify, what this actually comes out to be is negative 3 over x plus c. Now, at this stage, I challenge you to try something. Differentiate our result. Take negative 3 over x plus some constant and differentiate it. If you do it correctly, what you should end up with is our original integrand. So there we go. That's why I say the integral is the inverse of the derivative. Well, this second problem here is a little bit trickier, but go ahead and try it on your own before we move on. Pause the video and give it a shot. And when you're ready, come on back. All right, so assuming you've come on back, we can rewrite this by pulling the constant of 1/2 out of the way. And I'm actually going to distribute the x that's remaining. That's going to give us the integral of quantity x cubed plus 3x dx. And how do I integrate that? Well, once again, I leave my 1/2 on the outside, And each one of these I'm going to handle separately using the general power rule for integrals. That means this first term is going to turn into x to the fourth over 4, and this next term is simply going to turn into 3x squared over 2. And again, I'm going to be careful to keep the plus c with it. So, all good. Let me go ahead and distribute that 1/2 so I can find my simplified answer. That's simply going to be x to the fourth over 8 plus 3x squared over 4. And then here's the kicker, plus c. And of course, you're going to ask, well, why isn't it plus 1/2 c? Don't I need to distribute that half? And the answer is yes, absolutely, I need to distribute the half. But c represents some arbitrary constant. And we'll find out why it's there in the next example. But c is just a constant. We don't know what the constant is. So, if you multiply that constant by half, what do you get? Another constant. And that's why I just leave it at c. We could multiply c by 5. We could add c to pi or whatever. We're still going to get just some constant. So I'll leave that at plus c. So you see how we can take an original integrand and rewrite it in such a way that we can integrate it. This is the indefinite integral. It's an integral without bounds, and even though you don't know what that means, we'll go with it for now. And with that, let's go ahead and take a look at the next few examples in which we'll be finding more indefinite integrals. So that will be fun and exciting. In the next 4 examples, we're going to integrate an increasingly diverse series of integrands and hopefully learn something from each one. So we're going to start with this integral right here, the integral of x cubed to the 4th root plus 1 dx. Well, that looks like a giant mess, and I don't like giant messes, so I am going to rewrite this using a fractional exponent. I'm going to call this x to the 3/4 plus 1 dx. And I think that's going to be a lot easier to integrate because I can use the general power rule for integrals on this. If I do that, let's see, I have x to the 7/4. I just increased the exponent by 1, and I'm going to divide that by 7/4. Now, what am I going to do with this 1? Well, think about this. If you think of 1 as actually being x to the 0th power, which is reasonable to think about, when we integrate x to the 0th power using the general power rule, what we'll get is simply x to the 1st over 1. And what is x to the 1st over 1? That's just x. So that's pretty useful there. When I'm integrating a constant, I'm literally just going to put an x on it and be good to go. So that means this is just going to be plus x. Now, why do I need that plus c? I'm going to get into that in just a second, but first let's go ahead and further simplify this. Let's call this 4x to the 7/4 all over 7 plus x plus c. That is our final answer. It is correct. But following the directions, I now challenge you to differentiate this answer that we got. If you differentiate it, what do you think you're going to get? Do it real quick. You might be able to do this in your head. And if you do, don't you get back to our original problem? Well, here's something I want you to try real quick. Instead of doing plus c, what if we did 4x to the 7/4 over 7 plus x plus, choose a constant, any constant you like. How about negative 50 pi? That's a big constant. Differentiate that. And what are you going to get? Again, you're going to get our original integral. Well, choose any constant here, and you'll find that when you differentiate it, the constant just kind of cancels itself out anyhow. That's why we have to put a plus c. The plus c represents any constant we can think of, because when we differentiate it, it's gone. So what we actually get is a family of functions that are the solutions to these integrals. We can put any number we want for c, and this will be a correct answer. That's why we put plus c, to represent all those constants. So hopefully you got the idea. We will revisit this idea later, in fact, in these particular notes. But for now, let's move on to example C. Example C might scare you a little bit because it has sine of x in it, but let me show you that it's really no big deal. The first thing I'm going to do, of course, is to rewrite this integral, and I'm going to rewrite it as x to the negative 4th minus the sine of x. And I'm not going to forget my dx, of course. Now, when I use my general power rule for the first term, of course, I'm just going to get x to the negative third over negative 3. No big deal. But what's going to happen to this minus sine of x right here? Well, it's really no big deal. Let me remind you that the derivative of sine of x is just cosine of x. And let me remind you that the derivative of cosine of x is nothing more than just negative sine of x. These are both things that you remember from previous chapters. So if I use this information, if I want to integrate negative sine of x, what I'm actually doing is starting over here and going backwards. All right, so if I integrate negative sine of x, that's going to give me cosine. And that's perfect. This is negative sine of x right here, and the integral of that is just cosine x. Now, of course, don't forget your plus c. You will forget your plus c at some points, and you'll get points taken off if it's a test or quiz. So be very careful on your plus c. In fact, on the AP exam at the end of the year, points are available for nothing else than just saying plus c. So never forget that. Let's simplify this one little bit, and what we'll end up with is negative 1 over 3x cubed plus the cosine of x plus c. And I now challenge you, again, as before, differentiate this and see what you get. I bet it'll be our original integrand. And with that, let's take a look at example D. Before we do example D together, I challenge you to go ahead and try it yourself. Example D is actually very, very easy if you look at it the right way. So if you try to integrate it the way it stands right now, you really won't be able to do that. The power rule works if you have x to the nth power. But here we have this quantity 2t squared minus 1 to the second power, and that's just not going to work with the power rule. So pause the video, think about this for a second, try the problem out, and let's see if you get the correct answer. When you're ready, come on back. All right, so either you're back now or you decided not to try this on your own. Hopefully you're not scared about this problem. All you really need to do is just square this binomial. And if we do that, we'll see that this really is not that bad of a problem at all. We'll have 4t to the fourth minus 4t squared plus 1, if I'm squaring that correctly. And it looks like I am. So if we want to integrate this, no big deal. We have the power rule we can use. So check this out. We have 4t to the fifth power over 5. We'll have 4t to the third power over 3. And do you remember what to do when we have just a constant hanging out? Well, remember that we just put the variable on that one. So that turns into plus t. Let's include our constant of integration. And there is what I consider to be, anyway, a very simple example. Example E might not be so simple. But before we get to example E, take a look at it. See if there's anything you can simplify on it before you do the integration. And that might help you out if you want to try working that out yourself before we get to it together. Of course, we're going to get there right now. So example E is another tricky trig problem that really is not that tricky at all once you see it worked out. What we need to do is we actually need to simplify this expression here before we go about integrating it. So the numerator is going to say cosine x, but what's going to happen in the denominator? Hopefully you recognize that as that Pythagorean identity or whatever it's called, where this is clearly going to give us sine squared of x. Now, what can I do with this? This doesn't look like something simple to work with. However, if we rewrite it again, and if we consider this to actually be the cotangent of x multiplied by the cosecant of x, maybe that will help us, because that looks kind of familiar. Does that look familiar to you? It should. And if it doesn't, go back and look at your chapter 3 notes. Somewhere in there, we handled derivatives of some trig function that resulted in something that looked actually kind of like this. If you don't remember what it is, let me go ahead and refresh you real quick. If you recall, the derivative of cosecant x was actually negative cotangent x cosecant x. Now, is that the same as what we have here? Clearly, you can see it's very similar, but not exactly the same. However, if we introduce a negative sign right here, Now it is exactly the same as this. Problem is, can we just go around adding negative signs willy-nilly to whatever we feel like? Of course, the answer to that is no, but what we can do is multiply it by a -1. And so if we do that, we've multiplied it by two negatives. That didn't change anything, except it enabled the integral to look really, really familiar to us. And so what's going to happen here is this -1 that we introduced is going to come on down. And this integral that we've seen before is going to turn into our cosecant x. And so what we end up with here is actually negative cosecant x plus c. And you can see kind of how that works. It is tricky. It involves, one, a Pythagorean simplification right there. Two, we had to know how to split it into cotangent cosecant. And three, we had to recognize cotangent cosecant as almost one of the derivatives that we learned last chapter. Rest assured, as we make it through chapter 4, we will learn all the integrals of all these crazy things here. But for now, just go with your reverse derivative knowledge, if you will. Anyway, with all that being done, let's take a look at what the integral actually means. We're going to take a look in example F at the graph of a derivative. The graph of a derivative. And based on that graph, we're going to see if we can't recreate the family of original functions. Let's go ahead and take a look. So in example F, we're given the graph of the derivative, and we need to draw the original function. In fact, we need to draw two original functions that could result in the following derivative graph. So the way I'm going to do this is to actually create a table. And you don't have to do it this way. There's lots of ways of doing this. But what I'm going to do is separate this entire graph into two intervals. That's going to be -infinity up to 0, and then 0 up to positive infinity. And the reason I do that is I'm going to look at the behavior of the derivative. I'm going to look at the behavior of the second derivative, and then I'm going to try to make some conclusions based off of that. So let's take a look here. The first derivative on our interval from -infinity to 0, the first derivative is positive the entire time. It's always above the x-axis. It never seems to drop below. And so I can say that the first derivative is positive in this first interval right here. Now, in our second interval, what can you say about the derivative? Well, remember, this is a graph of the derivative. This is not the original function. So here we can say the graph is always positive, or in other words, the derivative is always positive. I know the graph is sloping down, but remember, this is a graph of the derivative. If the graph is positive, it's because the derivative is positive. So with that, let's take a look at the second derivative. Now remember, the second derivative is the rate of change of the first derivative. And being that this is the first derivative, we just need to look at whether it's increasing or decreasing for our second derivative. So in our first interval right here, we can see that the graph is certainly increasing. The first derivative is increasing, telling us that the second derivative is positive. Now on this other interval, the graph is decreasing. Yes, the derivative is always positive, but the derivative is decreasing. In other words, there is a negative second derivative. So this is all very confusing, but if we fill out this table, what we can reach as far as conclusions go, on our first interval, we're increasing and concave up. So we're going to look something like this. On our next interval, we're still increasing, but we're concave down. So we're going to look something like this. And do we ever connect in the middle? No, because clearly we have an asymptote here. So what is this going to look like? Very simply, I'm just going to redraw these two pictures on this graph. So one version that our original graph could look is this red one right here. This will be the left side of the graph. And then the right side of the graph might look something like this. And I'm just making up its location. It really could be anywhere vertically speaking, anywhere up or down, so long as the first derivative and second derivative are correct for it. In fact, let's take a look at one more graph that could be the original. Maybe it goes like this. In this graph, I'll draw in black. So you see, it matches the red graph pretty well. I'm just changing its vertical location. So maybe the left part goes something like that, and maybe the right part goes something like this. I don't know. we don't know exactly where it is vertically, and that's why we always need to put a plus c when we're doing an indefinite integral. So I'm having fun drawing these original functions, but I better stop and move on to the next example, where we're going to take a look at initial value problems. So these last couple examples are going to be initial value problems. These are also referred to as differential equations, and the reason for that is we're given a derivative that is essentially the differential of an original function, and so we just need to solve it, find the original function. Some physics notes that you might want to take here. If we consider f of x to be a position function, that is a function that describes where a particle is on a plane or on a number line or anything like that, we can take the derivative of that and get the rate of change of the position. And from physics, even just basic physics, you should know, what is the rate of change of the position? Well, that we refer to as velocity. Of course, velocity is just how something changes. So there we go. Now, what happens if we take the derivative of velocity? Then we're looking at how quickly the velocity changes. Think about when you start up your car and you start driving. At first, your velocity is 0. And then you increase to 25 miles an hour, and then perhaps 35 miles an hour. What's happening? Your velocity is changing. And why is your velocity changing? It's probably because you're stepping on the accelerator pedal. So the second derivative of position is simply acceleration, and that is the rate of change of velocity. Now, of course, we can go further and look at the third and fourth and fifth derivative and so on and so on. But any further than acceleration, I invite you to ask your physics teacher about that one, and we'll leave that alone for the sake of calculus. Now, all this being said, here we are given a velocity. The velocity is given as 6x squared, and we're told that the initial position, g of 0, the initial position is -1. Well, how is the initial position going to help us if what we're given is velocity? Quite simply, if we integrate the velocity, that is the integral of g prime of x dx, if we do that, that should give us simply g of x. And that's what we need. Now, if we integrate g prime of x, of course, the other side of that says 6x squared. And you can rewrite that and do whatever you got to do. Move the 6 out of the way and do the general power thing. However you want to go about this. What we should end up with is, in fact, 2x cubed plus c. And now we're going to see why that plus c is so important. See, we now have the position function. That's right here. G of x equals this. And we're told that the position at time 0 or at x0 or whatever the case, our position is -1. Well, let's see how that works. If I go ahead and actually plug 0 in for x, what I'm going to get is this right here, 2 times 0 cubed plus c. And of course, that should equal -1. -1 from right here. So, well, let's see. 0 cubed times 2, this whole thing cancels out. And what I end up with is that c is -1. And what does that tell me? Well, that tells me that my position equation, g of x, has to be 2x cubed minus 1. Now, let's go ahead and check and see if this actually makes sense. At g of 0, what is my value of g of 0? Plug that in, you'll find that g of 0 is -1, as given by our initial value here. And if we do the derivative, if we differentiate this position, what do we get for the velocity? Well, go ahead and differentiate it yourself, and you'll see that we get 6x squared, as given in the problem. So that's beautiful. Given the velocity, we found the position, we used the initial position to find our constant, and ended up with our final position function. What would have happened if we didn't put this plus c here? Well, we would have gotten 0 equals -1. That would have been all messed up and confusing and ridiculous. And so it's a good thing that we have that plus c. So we have one last example to try, example H. This one is going to involve them giving us the acceleration, and we're going to bring it down to position. Go ahead and try it before we get there, because we're going to get there really, really quick. So here is our last example. As promised, we are given an acceleration equation. We're told f double prime of x equals x squared. So No problem. We'll work with that. We're also told that our initial velocity is 6 and our initial position is 3. So these are all going to become very important as we work our way through this problem. Of course, the first thing I'm going to have to do is integrate the acceleration. By integrating the acceleration, what I'm going to end up with is the velocity, and hopefully that will be useful. So if I'm integrating f double prime, of course, the other side of that is x squared. And if I if I integrate that, of course, what I'll get is 1/3 x cubed plus c. And I'm actually going to call this c sub 1, because since I still have a derivative here, I know I'm going to have to integrate again. That'll introduce another constant, so I'll just call this one c1 for now, without loss of generality. Now, of course, I am given the initial velocity is 6. So if I go ahead and work with that, if I plug in 0 for x here, what I'll get is, well, plug 0 in for x, I get 1/3 0 cubed plus c sub 1. And I'm told that this needs to equal 6. So, well, this part is gone. And what am I left with? Simply c1 equals 6. So that must tell me that my original velocity equation is actually going to be 1/3 x cubed plus 6. Awesome. There is my velocity. What can I do with this? Well, I'm going to integrate my velocity. And when I integrate velocity, of course, what I'm going to get is my position. And that is what I'm looking for. So let me go ahead and rewrite all this stuff here. As you can see, I'm integrating the velocity, and that's going to give me f of x, the position. And over here, if I work with this, I'm actually going to get 1/12 x to the 4th. I'm going to get 6x, and finally, plus c sub 2 this time. So, once again, I am given the initial position, that's right here. Initial position is at 3. So, f of 0 is going to be 1/12 0 to the 4th power. Well, that's easy. I know what that's going to be. Plus 6 times 0, also pretty easy, plus c sub 2. And I know that all of that has to equal 3. So let me run through here. This is gone and this is gone. And look what I'm left with. C sub 2 equals 3. And so that tells me that my final position function is actually going to say 1/12 x to the 4th plus 6x plus 3. Can it really be that easy? Is this really correct? Well, plug in 0, see what you get for f of 0. It is 3. Differentiate it and plug in 0 to see what you get for the initial velocity. You will get 6. And differentiate the velocity, and you'll get the acceleration, which, according to this, is x squared. So there you go. Good times all around. And so, here in the first inaugural lesson of Chapter 4, we've done quite a few things. We started by looking at the power rule for integrals. We talked about how to rewrite an integral by moving the scalar out of the way, and then how to deal with the exponents. Remember what we said, you simply raise the exponent by 1 and put that as the denominator as well. And boom, there you go. There's your power rule for integrals. After that, we practiced some indefinite integrals. I really haven't explained to you what an indefinite integral is, but rest assured, that's what we've been working with so far. We'll get to definite integrals a little bit later. From there, we took a look at a graph of a derivative and found the original function. Essentially, we integrated graphically, if you want to look at it that way. We didn't know the algebra. We didn't have the function, so we couldn't integrate the function itself. But graphically, we came up with the original function that would have had the given graph as its derivative. That was a fun time. And then finally, at the end, we dealt with some differential equations. You can think of these as pseudo-physics applications. Certainly in physics, you've learned about the whole 9.8 t squared and all that stuff. And we're going to look at where that actually comes from later. But the idea has already been visited here in lesson 4.1. So remember all these things. There is a lot of stuff, but this is just the introduction. We're going to solidify this as we move on through chapter 4. So good luck with this assignment.